Welcome back again, and this is now EQ3 of Tectonic Processes and Hazards. And EQ3 outlines how successful is the management of tectonic hazards and disasters. So this is evaluating the success of management of the hazards we've looked at, really. Remember to use your hazards booklet that you've been given, and remember that you need to use your lesson notes too. This will not be enough. You may need to go back and look at those lesson notes to understand some of this theory and concept. Please do that. Let's get started straight away. First thing in EQ3 is to look at the trends of disasters tectonically since 1960. So, there's been no real change in overall deaths due to tectonic hazards since 1960. Each year, essentially, it varies considerably. So even though technology has come a long way, we still have no real change in overall deaths. For example, in 2012 and 14, there were fewer than 1,000 worldwide deaths due to tectonic hazards. But in 2004 and 2010, there were over 200,000 deaths in each of those years. And that's because what are called mega disasters, which we'll look at next, skew this data. If you have one really large disaster in a year, that will skew the data way upwards. So in 2004, for example, we had the Indian Ocean tsunami and earthquake. That will have skewed this data. Volcanic disasters are much less frequent than earthquake disasters, and deaths from eruptions are now rare. So volcanoes tend to cause much less deaths and are much frequent than earthquakes. Economic losses due to earthquakes continue to rise, averaging between 20 and 40 billion US dollars per year. This is because more people who are more affluent in the world have more property to lose. So as wealth increases in the world, the cost of replacing anything damaged also increases too. So there are the trends overall in tectonic disasters since the 1960s. I mentioned mega disasters before. Now, mega disasters are disasters that are on a large scale, economically, socially, etc. I'm going to give you 3 examples, and these are 3 of our case studies, so you can label those as mega disasters. The 2004 Indian Ocean tsunami. 14 countries overall were affected by this, and we had economic losses and deaths in a number of those countries, including Indonesia, Thailand, Sri Lanka, and Somalia, amongst others, which makes this disaster one of the largest disasters in terms of regional and aerial extent there ever has been. The 2011 tsunami in Tohoku, in Japan. Only Japan was affected for this, but the economic impacts had global consequences. We had disruption to ports, factories, and power supplies. Global car production slowed. Boeing jet production slowed. Electronic production in general slowed because Japan is one of the centers of excellence for technology. In addition, we had a nuclear meltdown disaster in Fukushima, which caused a radioactive leaking of a Fukushima power plant. And that led to Germany abandoning its nuclear energy program because of the risks involved in nuclear energy production. So again, even though it only affected Japan directly, actually it had worldwide impacts. And finally, the Eyjafjallajökull case study in 2010, the eruption in Iceland. Again, although actually the impacts in Iceland were quite narrow in the sense that there was no loss of life, it was well managed, actually it's considered a mega disaster because of the impact it had on all other nations around the world. So over 20 European countries were affected by a total or partial closure of their airspace. The airline industry was massively impacted. The ash cloud from the eruption itself traveled southwards towards Europe, and that meant that airlines couldn't fly because of the dangers of ash being ingested into the jet engines. And so therefore, we had over 100,000 cancelled flights and over £1 billion worth of losses in the airline industry alone. So there are just three examples from our case studies of how these three events are mega disasters. They must affect more than the country itself. And then in EQ3, you also looked at a multiple hazard zone. And we used the Philippines for this as the best example of a multiple hazard zone. Now, remember, what defines a multiple hazard zone is an area with complex disasters and multiple of them. They're usually tectonic hazards as well as hydrometeorological disasters. So, for example, an earthquake or a volcano and a tropical storm. As you can see there, tectonic hazards include earthquakes and volcanoes, tsunamis, and landslides. And hydrometeorological events include flooding, drought, storms, tropical cyclones, etc. Philippines has the following characteristics which makes it susceptible to hazard. So this is why it's a multiple hazard zone. It's very tectonically active, so earthquakes and volcanoes occur. It's geologically quite young as islands, and so it has unstable mountain zones, and they're prone to shifting. It's on major tropical storm tract. So major tropical storms move through this area. And also, it may suffer from global climate change, such as El Nino and La Nina oscillations, every 2 to 7 years. Just an example for you, in 1991 eruption of Mount Pinatubo, which is one of your case studies we mentioned earlier, in the Philippines, the area was also struck by Typhoon Yunga. So not only did it have the volcanic eruption, but it also had the heavy rainfall from Typhoon Yunga, and that created the destructive lahars that we saw in the secondary impact of the volcano. So this shows how we can link hydrometeorological hazards with tectonic hazards. Okay, so this is what causes the major impact you see in the Philippines. Now let's move on. We need to look at very briefly how we can or cannot predict earthquakes, volcanoes, and tsunamis. Let's start with earthquakes. Now, earthquakes, despite decades of research, cannot really be predicted. What we can do is identify patterns in how often they happen. We can't then predict when the next one will happen because they can happen at any point. So we can risk forecast, but we can't actually predict. We can say where is likely to suffer from liquefaction using land zoning, and we can therefore not build in those areas. But again, this is not true scientific fact. And we also have areas that are in what are called seismic gaps. So these are areas that haven't experienced an earthquake for some time and are, quote brackets, overdue. And that can point to an area being high risk. But what we do have is earthquake early warning systems, and you can see this in the image on the bottom here. So what we do is we have a sensor in, let's say, the ocean or on landscape on an area. And that sensor is triggered when there is a wave or a P wave, if you like, felt. That sensor sends information to an earthquake alert center, and that sends information to people's mobile phones, messages, etc., so that they can be warned that there may be an earthquake imminent. But that doesn't, again, predict, that only gives warning when it's happening. Volcanoes. Volcanoes are much easier to predict. We have lots of ways in which we can predict volcanoes. If you have a look at the graphic at the bottom, we can monitor the gas coming out of the crater. We can use remote sensing to look at satellite images, thermal imaging. We can use cameras. We can look at the shape of the land to see if there's any bulge taking place. We can use a deformation scale such as tilt meters and GPS and surveying to see those changes on the landscape. And we can also measure ground vibrations, small earthquakes, which usually point towards a volcanic eruption taking place, using seismometers, lahar sensors, etc. So, because we've got very sophisticated monitoring equipment, as I've just mentioned, we can actually predict when a volcano is likely to erupt. And the minimal death toll from volcanic eruptions, even though there is 60 to 80 worldwide a year, can be attributed to the technology and the prediction we have for volcanoes. So our prediction for volcanoes actually has led to less deaths as a result. And finally, tsunamis. So we can partly predict tsunamis. An earthquake-induced tsunami can't really be predicted. So a tsunami that's caused by an earthquake is hard to predict because we don't know when the earthquake will happen. However, what we can do is very similar to the early warning systems for earthquakes. We can have tsunami warning systems. So we can have seismometers tell us an earthquake has occurred. We can locate where that's been occurred. And if it's been in the open sea, then we know that there is a chance that a tsunami is possible. And you can see there, we have the buoy system, right? So we've got a recorder on the seabed that records and detects tsunami differences, or sorry, it records and detects earthquake changes and earth movement. The buoy then takes that information from it and transpons it to satellites, and that transpons it to towns and cities and earthquake and tsunami centers. So we can partly predict tsunamis. Now we're back to theoretical frameworks again. So we're back to those theories we looked at in EQ3. So the hazard management cycle, you've got an image of that on your booklet, okay? And there are 4 stages involved. So when a hazard happens, we've then got response, recovery, mitigation, and preparedness. So let's go through each of those. What is the response phase? This is the immediate help to rescue lives and save lives. It's the aid immediately to help keep people alive. It's emergency food, water, and shelter. This often comes from government, international organizations, and also comes from NGOs or non-governmental organizations like charities. We then have the recovery phase, and this is where we try to rebuild infrastructure and services. We try to treat the injured and rehabilitate them mentally and physically and try to get them back to normal life. We then have the mitigation phase, which is where we're thinking about the next hazard potentially, and we're trying to reduce the problems that the next hazard creates. So we might start to use land use zoning, where we say that there are certain areas that will not be built on again. We might build hazard-proof or resistant buildings, like earthquake-proof buildings. We might improve infrastructure. And then finally, we have preparedness. So this has got to do with, for example, education in the community, resilience building, making sure people know how to act rationally, predicting, evacuation technology and systems, etc. So all of these things are preparing for a potential hazard next. So that is the hazard management cycle, and that's how generally a hazard should be managed for a process. Now, the recovery stage can be considered as I mentioned earlier, returning to normal. But this takes varying timescales depending on how big the event was, the development level of an area, the governance of an area, and the external efforts in terms of aid. So Haiti, for example, the 2010 earthquake, they are still in the recovery stage today, 10 years later. However, Iceland, during the Eyjafjallajökull eruption, went through the recovery stage within a few months, rebuilt the roads, etc. The next theoretical framework we had was the Parkes disaster model of response. So the Park model, as you can see on the right-hand side here, looks different depending on which diagram you might look at. I've chosen the one with 3 lines for you. The one with just 1 line would be this red one. Okay? I've chosen the variations in Park 1 to show you because you need to understand the differences in terms of development and recovery as well. So the park model essentially illustrates the possible outcomes of a natural disaster hazard. There are potential variations within the park model, and they're seen on the right through A, B, and C. And this depends on the level of development, how good the response is, how good the relief effort is, and that creates varying levels of resilience and recovery. So essentially, different places, different levels of development will react differently to hazards and will develop and recover differently. The curve A there, you can see it's color coded, shows a disaster with a relative impact on quality of life and an average response phase. Quality of life begins to improve steadily and returns to normal within a few months to a year. Curve B shows a very highly developed area where quality of life is less impacted. Reconstruction takes a small amount of time. Mitigation improves the quality of life, and the community is better prepared for next time. And finally, then, curve C shows a very impoverished area, like Haiti, where the actual hazard has a serious and long-term impact on the quality of life. Reconstruction is very slow, and they do not recover to the previous levels of quality of life they had. So in Haiti, for example, as we said, it fits profile C, and the reason for that is because they have not recovered incomes to where they were before the quake. They've also not recovered healthcare. School provisions are still poor. There's more people under the poverty line than there was before the hazard, and so on. Whereas A and B are more likely to be developed nations that have more income, better healthcare, and so on. So one of the final things we need to look at is disaster modification. So how we can modify different aspects to try and reduce the impacts of these events. So first of all, we've got modifying the event itself. So trying to modify the earthquake or volcano or tsunami. And there's a number of things we can do. We can use what's called land use zoning. So we can stop building on coastlines or close to volcanoes. This is low cost, but it does require strict legal enforcement. We can build earthquake resistant buildings. And they have deep foundations and they have reinforced steel, so they're very sturdy, but they are very expensive. So only a number of places around the world can afford to build these. We can build tsunami defenses, such as sea walls, and they dramatically reduce damage from tsunamis, but they can be overtopped, so the water can just go over the top of them if they're not high enough. And we can also do what's called lava diversion, and that basically diverts lava away from towns and cities from volcanoes. And this is relatively low cost. It just involves changing the channels in which the lava would flow down a mountainside, but it only works on small volcanoes. So that's modifying the event itself. We can also try and modify the vulnerability of people, communities, and countries through high-tech monitoring, which predicts volcanoes, but it's very difficult to be successful, and it's costly, so it doesn't actually prevent damage overall. We can have community preparedness and education, so schools can practice drills. They can prepare earthquake kits. It's low cost, it saves lives, but it doesn't prevent the damage itself from happening. And we can also try and adapt by moving to safer areas. And that saves lives and properties, but high population densities prevent it from happening in a successful manner. That's how we can try and modify our vulnerability to these hazards. Finally, we can try and also modify or change our loss of life. So what we can try and do is we can have short-term aid, emergency aid, so food, shelter, and water. This does reduce death toll dramatically if it happened, but it has a high cost and it's difficult to access. We can also use long-term aid through reconstruction, and that possibly improves resilience as well for the next potential hazard. However, the costs of this type of long-term aid are very high. And finally, we can also, as individuals, have insurance policies. And we can have compensation for the individual losses we incur, such as damage to our housing. This does allow people to recover economically quite quickly, but it doesn't save any lives. It's not always available, especially if you're in a underdeveloped nation or a poorer nation. And therefore, it doesn't actually modify loss very well in terms of humans. It just modifies economic loss. So modifying the event, modifying vulnerability, and modifying loss are the ways in which we can try to modify disasters. And finally, over to you now. I'm going to leave you to do the last section yourself. You need to do some work yourself. So I want you to choose two major case studies, and you will see this in your booklet, and complete a management or modification evaluation for them in terms of modifying the event, the vulnerability, and the loss. So you're going to look at how two case studies have modified the event, modified the vulnerability, and modified the loss. And I've listed for you at the bottom there your 6 case studies. So you can choose any 2 of these. Try and make one poorer and one richer. So try and pick, for example, Ayafle versus Haiti. And I want you to just note down the ways in which they've tried to, in those nations, modify the event, modify the vulnerability, and modify the loss. That should take you about 15 to 20 minutes to complete. I hope you found that useful. That is the end of EQ3. Please make sure that you use all of these 3 EQ GeogPods to revise the tectonic section. Remember, as I said in the first EQ recording, that hazards is only worth 16 marks of your total A-level course. It's not a huge worth in the exam paper, but it is a very large topic in knowledge terms. So know the basics, know them well, pick out all of the information in the exam, and you will do just fine in the hazard section.